Hi, thanks for coming. So I will talk about understanding Numba, the Python and Numpy compiler. And I want to be clear at the start, like I don't really understand Number. So I'm a gamma ray astronomer from Heidelberg. I'm not a Numba compiler or CPU expert. I recently started using it and I think it's awesome and I wanted to introduce it to you. So let me talk a little bit about how we use Numba and why we use it. So in gamma ray astronomy, we have these telescopes like the HESS telescopes in Namibia or the Cherenkov telescopes array in Chile. And there we have to do lots of numerical computing for data calibration, reduction, analysis. And we need both interactive data and method exploration and then production pipelines. And also the software is often written by astronomers, not professional programmers. And traditionally, the approach was, for example, for HESS for the past decade to write everything in C++, also using the root software from CERN, and then maybe have a little bit of Python scripting on top. And now it's different. Now we're trying to build everything in Python and Numpy, and then when needed for performance, we write a little bit of Numba, Python, or C or C++, so it's a different approach. For the CTA software, we're prototyping it using this Python first approach, and you see the stack, like it's based on Python and then the PyData ecosystem. So you have NumPy, SciPy, and so on. In astronomy, we also have AstroPy, which is the base library, which contains the standard data formats and time handling, coordinates handling, and so on for astronomers. And then on top of this, we can implement the gamma ray analysis software. And this approach is not really unique to what we do in our project. It's kind of become the standard in astronomy. As you can see in this graph here, Python is really now the most popular language to use in astronomy. And as Perry Greenfield points out, like one reason is that Python is a language that is very powerful for developers, for professional developers, but it is also accessible to astronomers. And this makes for a good mix. And I have two other quotes from Jake Vanderplas from the Python keynote at 2017 in the same vein, saying for scientific data exploration, speed of development is primary and speed of execution is secondary. And also in Python, we have these libraries for nearly everything, and Python is the glue that combines the scientific codes together. So we have these thousands of Python packages that implement all kinds of methods. Why do we need Numba actually? I mean, some algorithms are hard to write in Python and Numpy. Here's an example of a function computing one step in this game of life. I don't know if you're aware of this, but you have this update rule, whether cells live or die. And you can write it in NumPy, but then you have to write this double numpy.roll call, and the code is really hard to write and hard to read and hard to maintain. So this would be a case where just writing a for loop is simpler, and then if you write it in Python, it's inefficient, and then writing in C and wrapping it from Python can be tedious. So this would be a good case where you would go to Numba. And there's also a quote from Stan Seibert from the Numba team, just saying, like, don't write such NumPy haikus. If Python for loops are simpler, then write loops and use Numba. Okay, so let me introduce Numba. What is it? I mean, to find out more, go to the webpage, numbapydata.org. The tagline is Numba makes Python code fast, and it's an open source JIT compiler that translates a subset of Python and NumPy code into fast machine code. And actually later in the talk, I'll try to unwrap that statement and explain what it means. But first, let's see a little bit. The name Numba comes from the combination of NumPy and Mamba. So you do number crunching in Python, and it's then fast like Mambas. So Mambas are apparently some of the fastest snakes in the world. This is where the name comes from. And then how do you use it? Let's assume you have some function doing math, like here, using this Monte Carlo method to compute the number pi, where you just throw random points in the unit square and then check which ones are x squared plus y squared less than 1, so which ones are in the circle, and you count. And that's one way to compute pi. And if you do this in Python, it's extremely slow for a million numbers, because what Python does is that every number is represented by a pi object, and then to do the actual computation, what happens in something like x squared or less than 1 and so on, always you take the pi object and you figure out that it's an integer, look at the integer inside, then do the operation and the computation, and then create another Py object. So you have all of this overhead that makes math from Python really slow. To speed it up with Numba, it's very easy. You just import Numba and add number.jit decorator to your function, and then in this case it's 30 times faster. So this is how you tell Numba to JIT your function. Numba also understands NumPy, so in this case I have two arrays, x and y, which are like large NumPy arrays, and I do the same computation by passing them into a Monte Carlo Pi method, and then uses a NumPy array expression to do the same computation. And this is faster than using Python, but it also uses much more memory. But again, you can add the number.jit decorator and it will run faster, because what Numba can do is it can avoid these temporary array copies. So when NumPy sees x squared, it creates a new NumPy array, which is x squared. And creating these new arrays and allocating them and processing them is some overhead, which can be avoided if you compile down to machine code. And that's why Numba in this case is faster. If you want, you can also write the same function using a for loop, so it's really up to you. In this case, writing a NumPy array expression is more convenient, but sometimes writing a for loop is more convenient. And Numba will compile your code either way into optimized machine code. So kind of the evolution of a scientific programmer coming to Python is that maybe you start out with C or Fortran and you write loops all the time to do your data processing. Then you come to Python and you figure out that loops are 100 times slower, and you learn that you have to write everything as NumPy array expressions. But actually now that we have Numba, writing for loops is okay again. So it's a bit of a regression. What are the limitations of Numba? Numba compiles individual functions. It does not compile whole programs like PyPy. Numba only supports a subset of Python. It has some support for dictionary, list, and sets, but you cannot have mixed types of keys and values and all of the operations. Like some things, some Python data structures just cannot be efficiently processed and translated to machine code. And you see an example of this on the left side, where I have a list with mixed data types of a string and an integer. And actually, Numba is not able to compile this to efficient machine code. And what you get is you get a typing error if you try this. Also, Numba only supports a subset of NumPy. I mean, this is ever growing, but not all functions and all arguments to those functions are available. So you have to see. And also, I mean, Numba does not support any kind of Python code. Like, you cannot use pandas or scikit-learn or the requests library or these kind of things from your Python function, because Numba will not know how to translate that into machine code. It's really focused on math and numerics code. So a little bit more about these two JIT modes, the object mode and the no Python mode. If you add the number.jit decorator and you have some function which cannot be efficiently compiled to machine code, what will happen is that you get a Numba warning saying the compilation is falling back to object mode, but it will still run and give you the result. And what's happening under the hood is that all that happened was that Numba translated this function into something that's equivalent what the CPython interpreter would execute, where you still have Py objects and Python C API calls, and you get the same performance as if you only used Python without Numba at all. So 99% of the time, this is not what you want. And to make it more obvious when you write functions which cannot be compiled efficiently, you can use this no Python equals true thing, and then you will directly get a typing error saying failed to compile in no Python mode. And there's a shortcut, because typing number.jit no Python equals true is long. You can also type number.njit. If you actually do have a function where you need to go back and interact with the Python interpreter and Python objects, you can. And for this, you use the number.object mode context manager. This is rarely needed, but it can be useful if you have like a long-running function and you want to log the progress or update a Python progress bar, which is a Python object. Then you can say with number.object mode, and inside this with statement, you can again interact with your Python session. Okay, so now let's come to the part where we try to understand what Numba does at least a little bit. So the description kind of is Numba is a type specializing JIT compiler from Python for Python bytecode using LLVM. And this might make your head explode, but let's try to unwrap that a little bit. There's really 3 parts involved here. What's going on when you write a function and you JIT it and you call it. And the first part is Python itself, and then you have Numba, and then you have LLVM in the background. And I'll explain on the next slides how these interact. So what the Python compiler does, it starts with your source code, parses it into an abstract syntax tree, and then transforms it to bytecode. And this happens on import of a module, like when the Python interpreter sees the def statement, it creates this, this function object and attaches the bytecode to the function object, which, as you can see here on the left. And then what Numba can do is it can start with this bytecode and compile and transform it to machine code, and that's what the number.jit decorator does. Actually, when number.jit decorator is called, it does very little. All it does is it creates a CPU dispatcher proxy object because it cannot compile the function yet because it doesn't know what types come in and what kind of machine code it should generate. So only when the function is called, it will then JIT compile the bytecode to LLVMIR exactly for those input types. And then it will also manage the LLVM compilation and execute the compiled function for you. So what is LLVM? LLVM is a compiler infrastructure project. There's many front ends for languages like C, C++, Fortran, Haskell, Rust, Julia, Swift, and so on. There's also many back ends for all kinds of hardware, so all the different CPU types. The vendors have added support for it and optimized it well. And you could consider Numba just to be the Python front end for LLVM. So the way this works is that LLVM is shipped as a Python package called LLVM Lite that Numba depends on, and this is maintained by the Numba team at Anaconda that then ships Numba and LLVM Lite so that it's readily available. Concerning alternatives, I mean, at least for us, like the most obvious one and what people also use is Python. And like Numba, Python is often used to speed up numeric Python code. Python is an ahead-of-time compiler where you have to type annotate your Python code and then it compiles to C, and then you use a C compiler to compile this to machine code. It's more widely used at this point. It's easier to debug because C code, generated C code is easier to debug than LLVMIR code, which is lower level and looks more like assembler code, and probably very few Python people can read and debug this. And also Python is very good at interfacing with C and C++ code. I mean, Numba, on the other hand, is easier to use. You don't have to add type annotations. You don't need to have a C compiler, but it is harder to debug. Another advantage of Numba is that it optimizes just in time for your CPU and GPU, so you don't need to build and distribute binaries for many architectures. Instead, it will always use all of the CPU features you have, like advanced processor instructions and so on. Other Numba alternatives, I mean, Python is great, and there are many other great tools that exist for high-performance computing in Python. So you have Python, C, C++, and PyBind 11 if you want to go the Python C extension way. There's PyPy, which is an alternative to CPython, which JIT compiles the whole program. And then you have all of these modern things like TensorFlow, JAX, PyTorch, and Dask, and so on, that similarly to Numba also use Python and Numpy mainly as the language to specify what kind of computation should happen, but then they will do some kind of compilations and execute it in various ways. And I don't have time and also don't have the expertise to explain all of the differences, how JAX and TensorFlow and so on compares to Numba and how exactly they compile. But you have to make a choice there. And it's not easy because there's many great libraries now available in Python. Okay, so some more things about Numba. One thing you should know about is number.s or number --sysinfo from the command line. Or you can also use it from IPython and Jupyter. If you just put the exclamation mark in front, you can execute shell commands, so you can also get the info from there. And as you can see here on the left, this gives you all of the relevant information about the hardware on your computer, like what CPU and GPU you have, which Python version, Numba version, and LLVM version you're using, whether you have the Intel short vector math library installed. I'll talk more about this later. Whether you have the Intel threading building blocks library installed, which will make Numba faster in some cases also, and then which GPUs you have available and GPU drivers you have installed. One thing you can do if you have a multi-core CPU and want to make your computation run faster is to add the parallel equals true option to the number.jit call, and this will then do multi-threading using one of the backends, either OpenMP, threading building blocks, or a custom one. If you want to use TBB, you have to do this conda install TBB in addition. And then, as shown in this example, it will work automatically for NumPy array expressions. There's no code changes needed. So in this case, I got a 3.2 speed up on my 4-core CPU for this computation by parallelizing it. If you have for loops inside of your function, you should use the number.prange generator, I guess. And then what will happen is the same thing, that Numba will parallelize this loop, and you will get the speed up from using multiple cores or also vector instructions. And what I show here on the lower right is just always like when you have Python decorators, you can use them in two ways. You can either put them with the add sign on top of your function, and the decorator will be automatically applied. Or you can just write your function without the decorator and then apply the decorator after by just passing the function into the decorator. So you can say number.jit, pass in the compute function, or you can say number.jit parallel equals true, this is a decorator, and you can pass in the compute function. And this can be convenient if you want to try out different options to compile the same function, so you don't have to always copy and paste the code of the function also. Another option you have is fastmath equals true, and there you can trade accuracy for speed for some computations. So there is this IEEE floating point standard that, in this case, for example, requires that the loop must accumulate these numbers in order to get a precisely defined result. But if you're willing to give this up and have a little bit of different accuracy, then the computation can go faster because the compiler can vectorize this reduction. There's another way you can speed up math functions. So if you have code that has square root, sine, exponential, and so on, then you can conda install the ICCRT package, and this will make these Intel short vector math libraries functions available, and Numba will tell LLVM to use those. And these are just like much faster implementations of these math functions. So that's how you get fast math. You might ask, like, how fast is Numba? I would say Numba gives very good performance, and there are many options to tweak the computation, but there is no simple answer to this question. And there is also no simple answer to the question of like how Numba compares to Python, Cython, NumPy, C, Fortran, and so on. You can find many blog posts on the internet, and they all have different outcomes depending on what application they do and compiler flags they use and what hardware they have. They get different speeds for different tools. And we've already seen this for Numba on the previous slides. The speed up is not always the same. So what you have to do is, if you care about performance, you start by finding a benchmark for your application that you really care about, where you have a performance bottleneck, and then you measure, and then you try to improve it. Another thing I wanted to introduce are NumPy ufuncs, or universal functions. So these are functions like add, sign, and so on from NumPy itself. And these all support array broadcasting, which you can see here on the left side. So you cannot just multiply two numbers. You can also multiply a number with an array, and it will broadcast these inputs and generate an output array. And there's a more complex example here. And then they also have these special methods attached, like accumulate, which apply it to one element at a time and accumulate it, giving a different output array. And so far, if you wanted to make one of these ufuncs, you had to write C code and use the NumPy C API, which was pretty hard. And now with Numba, it's really easy. You use the number.vectorize decorator, and it will make the ufunc for you. So the way you write your function is you don't put a for loop. You just write the operation for one element, and then the implicit for loop to loop over arrays and do broadcasting and so on. This will be generated by Numba for you. There's two ways to do it. You can give the type signature in the vectorized call, like I do here. I say, please make a ufunc, assuming the inputs are integer numbers. And then Numba will generate one ufunc on the vectorized call. If you don't give a signature, then again, such a dispatcher object is created. And then dynamically, when you call the ufunc, when you call the function, Numba will generate ufuncs for the input types you passed. So it will generate a different one if you put a float, pass a float input array or an integer input array. Okay, so I'm almost done already. So Numba is really a family of compilers. I've talked about two, number.jit for regular functions and number.vectorize for ufuncs. And just given a quick introduction to those, if you want to learn more, then check out the Numba documentation. There is also the GeoVectorize decorator, which can make generalized ufuncs. There is the stencil for neighborhood computation. So if you want to do some kind of convolution or sliding window computation, it's easy with the stencil decorator. There is cfunc, which can generate functions with well-defined C callback ABI. So this could be useful, for example, if you want to call a number function that you write in Python from C or C++ code. So if like all of your application runs in C++, but then you want to extend it with Python, then this would be one way to do it. And then there are these CUDA-JIT and RockJIT decorators to work with GPUs also. So just as a last point, who uses Numba? So Jake Vanderplas, again, wrote a few blog posts in 2013, when the project was still very young, saying, I'm becoming more and more convinced that Numba is the future of fast scientific computing in Python. This has not really happened so far. And then in 2018, Matthew Rocklin wrote an article advocating for the numeric Python community should consider adopting Numba more. So I think currently many people and applications use Numba for their work in projects like we do for gamma ray astronomy and many others do as well. But then the large libraries like NumPy, SciPy, Pandas, and scikit-learn have not adopted Numba yet. There are some nice examples now of libraries or packages using Numba, for example, DataShader, which is shown on the top left, which is a large data visualization library, is implementing their stuff in Numba. There's librosa, which is for digital signal processing and audio and music analysis, is implemented using Numba. And Intel has written HPAD, which is the high performance toolkit, and this can do big data processing and supports pandas. So they've done something very similar to what Numba did. They've defined a decorator, hpad.jit, which can take a function which does I/O and then NumPy or pandas computations and so on, and it will parallelize this also to clusters using MPI. So my summary and conclusions are that, Numba is a type-specializing JIT compiler for Python bytecode to LLVMIR. The project started in 2012. The current version is 0.44, and I think they're well on their way to version 1.0. It will use your CPU and GPU well, and it's really easy to use. You just have to add this Python decorator. So use number.jit for normal functions, number.vectorize to make ufuncs, and use Numba -s to check your machine and installation. If you don't find you get good performance or it's not working. And then if you want to use multi-core CPU and get fast results, consider putting parallel equals true and fastmass equals true, and also installing this as a SVML package. And I'm not a Numba developer. I didn't do anything to make this work. I just wanted to thank the Numba developers at Anaconda and also the other people and companies that have contributed, like, for example, Intel.
Very cool. Thank you for the great talk. We have 5 minutes for questions. Again, we have microphones over there. If you have a question, just line up behind the microphone and ask away.
Hi, thank you for the talk. How would you recommend packaging your package that uses Numba. Would it depend on the LLVM chain on the target machines where you install it, or?
No, I mean, basically you don't have to do anything. Like you have a pure Python package and you just put in your setup.py or into your dependencies, you put number, and that's all you do. And then pip or conda will automatically, I mean, Numba and LLVM Lite automatically ship with conda with the base installation, but you can also pip and conda install them. So if you put Numba as a dependencies, when someone installs your package, they will always get it. And you just kind of have a pure Python package, and you don't have to build wheels or binary distributions or do complex things. It's really easy.
Okay, thank you.
All right, any other question? Okay, excellent.
Thanks for the talk. Yeah, that was really awesome. I just wanted to know, like, what do you think are some of the reasons that the adoption of Numba is probably a bit slower than some may have expected?
I guess it took longer to reach 1.0 than they thought, and projects wait for 1.0 and stability. I mean, Numba has been amazingly stable for the past 5 years, I think, also, but it's still constantly improving. It is a bit scary if like, for example, say NumPy itself or SciPy, they could get rid of a lot of code if they adopted Numba and do things much more easily, like implement all of their ufuncs and this kind of stuff. But then it would be all in, like they would depend on LLVM Lite and Numba, and this would have to run and be stable for the next decade on all the supported platforms. So I know, for example, that on the NumPy mailing list, like 3 years ago, there was a discussion whether to use Numba as a dependency for NumPy, and at the time, people said no, mainly because, for example, ARM processor support was not there yet. And in the past years, the Numba team has added this and is testing really on a large range of hardware, and it's getting better and better, and I think it will happen. I don't know how fast it will happen, but I think projects will start to adopt Numba more and more.
Cool, thank you.
Cool. Let's go this side and then go back to that side.
I have a question about the other case study for using C++ code. So could I use a just-in-time compiled function in Python to call my C++ library using Numba? Is there some support for that?
I have to admit, I don't know. So this is something where Python really shines.
Yeah.
You can call any C and
sure.
C++ code. I have not done this myself. I think there are ways to call into a C library. I mean, but I have to pass on that. Check the documentation, please.
Right, thanks.
Over there.
I have a question. First of all, thank you for your talk. I've started using Numba a bit and discovered PyPy, and I was wondering, in a scenario where you have let's say you have multiple functions, one after each other, what is the overhead if you put a Numba at numba.jet before each functions versus compiling or using the whole code with PyPy? Is there a difference, or?
I'm not sure. I think it depends. I mean, for the cases where we are using Numba, like this overhead of JIT compiling the function does not matter at all. Like these milliseconds that are spent once to compile my functions, I really don't care about, even if it would take a second, and then my analysis runs for an hour and is really fast. I mean, if you have thousands of little functions that you need to JIT compile, then, and you have very short running processes, then this might become relevant. And I don't know how PyPy compares in terms of like the JIT speed compared to Numba.
So maybe what you're saying is that at the initialization of your module, it's not at that time where the compilation is happening, it's during the execution.
Yeah, so you have the overhead of starting up LLVM and doing the compilation, and I mean, if you look at this, so basically this is what's here. I mean, you see this chain of things that happen, and some things are done by Numba and some things are done by LLVM. But overall, this is very fast, like for a given function. But if you have thousands of functions and they're really long and complex, and you use like high optimization options for LLVM, then this can take, I guess, seconds or minutes in extreme cases. I don't know. But I never was in the case where this matters.
Okay.
Thank you.
Thank you very much. We are running out of time. You can chat with the speaker during lunch and the conference. And thank you very much. Let's thank all the speakers.